What if the next engineering breakthrough never makes it to the test bench? Because it doesn't need to. In today's episode, we're joined by Derik Cloete, a Senior Engineering Solutions Manager at Leap Australia. Derik is more than just a simulations expert. He's an advocate for building things that haven't been built yet, using physics, code, and compute. We explore how digital prototyping is reframing the way engineers design, test, and iterate, not after failure, but before the first cut of steel. From CFD to FEA to digital mission engineering, we unpack these acronyms and, more importantly, the thinking that lets engineers rehearse reality before committing the resources. But this just isn't about faster development or fewer prototypes. It's about what happens when we stop seeing simulation as a specialist tool and start treating it as the core design mindset. So here's the question. If you could model anything, flows, forces, particles, even the mission itself, what would you build next? Welcome to the Structural Intelligence Podcast, the show where we explore the intersection of engineering, technology, and innovation. I'm your host, Owen Keenan, structural engineer, entrepreneur, and tech enthusiast. Each episode brings together innovators, experts, and thought leaders who are pushing the boundaries of what's possible in engineering and technology. Through deep conversations and practical insights, we explore how new tools, techniques, and mindsets are reshaping our industry. We hope you enjoy this episode. So Derik, welcome to the show.
Thanks. It's good to be here.
It's good. Well, I've given you a bit of an introduction, but I'd love to hear from yourself. You're in your own words. Your journey and other things. So.
I loved hearing that you're a tech enthusiast. Yep. I would say I'm a tech evangelist.
Great.
That's what I do for a living, really. I am an engineer. I'm a mechanical engineer. Graduated out of University of Pretoria in South Africa. Mm-hmm. My dad wanted me to become an electronics engineer, but I didn't have enough faith for that, because you have to believe that electrons move around on a circuit. You can't really see them. Well, these days, I guess you can. You've got instrumentation to do that possibly. But mechanical engineering is a bit more hands-on. You can see and feel and look at and throw things around and see what happens.
Yeah, definitely.
And in the early part of my career, I was thrown into the experimental test and measurement world in the deep end. Really, it was really a lot of fun to be able to go down to the test lab or go down to a proofing track, for example, and stick some sensors on a structure. Switch on the recorder, sometimes a video camera as well, to kind of capture what's happening while you're recording your signals, and then come back and build some kind of a simulation model to replicate the same thing, and then to see the correlation. As a brand new engineer, having just studied all of these concepts, applied mathematics, applied physics, and all those kind of things, be able to actually do the calculations by hand, and the responses you get from your strain gauges or accelerometers are the same thing, or at least within a believable tolerance of each other.
Yeah, so you got a bit of a flavor in your early career. I love that sort of stuff, like being able to see the physics in action is a huge thing. But continue. What are some of those things that I guess stood out to you as you developed at that stage? It's this whole idea, I guess it's the scientific method, right? Where we can do things and repeatedly get the same answer. If you're able to replicate someone else's work, there's a lot of confidence in the fact that this all works, right? So that made me passionate about this whole idea of being able to make designs, prototype them virtually, go build a prototype to test your model, your simulation, the thing on the computer, so that you've got this gained knowledge and trust of how this thing is going to be operating and performing in the real world. That just makes me passionate. Yeah. And so I kind of share that passion with people these days. I moved out of a hard technical role probably about 6 years ago. Yep.
I would say I'm now in a soft technical role.
Yeah, right.
So more in a sometimes advisory kind of capacity, or sometimes just listening to people's problems that I totally do not necessarily comprehend all the physics on.
Yeah, that's right. That's right.
I'm a mechanical engineer. I wouldn't say structural as such, but mechanical in the sense of, I'm worried about things that are mostly in the solid phase, not so much liquid and gases.
Yeah, that's right. Yeah.
I do have a passion for those things as well, but as an enthusiast, not as a knowledgeable expert as such. So, but I'm fortunate. A lot of my colleagues are experts in those fields. So I get to sit in discussions with customers, listening to problems that they describe to us, and hear how my colleagues would approach it and how they would set up a complex multi-phase fluid dynamic study to understand what's happening.
Yeah, I suppose let's jump into that. So your role with Leap, what does that entail, and what are some of the things that you guys do?
Well, customers usually come to us saying there's something that we have to build or design or prototype or something like that, and we're concerned about this aspect of it. And they would do their best to describe the problem. Sometimes the customers that we're dealing with, or future customers that we're dealing with, might have never seen simulation at work. They might have heard about it or seen other people do it, but they've never actually played with it themselves. And maybe not just played, but actually use it in anger as well to solve problems. Yeah. And so we often go in and listen to the way that they describe the problem, reformulate it in a way that we can apply it to software, and build a numerical model that describes the same behavior, because we have the physics captured in the software, right? That's the whole point of having a model. And then we map out a pathway forward with the customer to say, ultimately we're interested to help them do this themselves. Sometimes that entails us having to do some work for them up front, to kind of prove the concept. But ultimately our goal is to make fishermen instead of catch the fish and share it.
Yeah, that's it. So I suppose to break it down, you're talking about simulation. And so that's something that we've talked about recently, and it's been quite interesting to see that. And obviously we'll jump into the detail of that sort of thing. But stepping back a little bit, just thinking about how you described your early stages in your career and how you were sort of doing the calculations. It might have been hand calcs, it might have been other things, and then jumping in and seeing the response in a real life form. I reflect upon that, and what that really sees to me is that's the physics of the world. Physics that we've been able to demonstrate, over the concepts of many generations to understand how the physical world works. Yeah. And I'd love to jump into that a little bit and how you feel about sort of the different types of physics and things involved, because I think that plays a good little bit of a context to jumping into, okay, what does it take to maybe simulate some of those things? But I'm a bit of a geek for physics, actually. But yeah, from your perspective, how do you see that in terms of the physical world and how systems work and other things? What's your approach?
I listen to a lot of interesting people, and the debate is out whether we are in a simulation or if this is in fact reality.
Interesting, actually.
That was just a joke.
Here we are talking about simulation in a simulation. That's pretty funny.
Yeah.
So
this is the Matrix.
Yeah, this is it.
I mean, the things that drive customers, I'm very customer facing, right? So I'm always trying to solve problems that a company faces for whatever the thing is that's causing them pain. And different things cause different people different pain points, I guess. But most often it's because something's going to cost too much, it's going to take too long to develop, or something failed and someone got hurt, or some equipment got hurt, or the potential for something to go wrong. So we're talking about risk management and those kind of things. And people want to get a handle on what's going to happen before something goes seriously wrong.
Yeah.
So whether it is overspending on a budget, or whether it is safety, functional safety or hazard, or those kind of things, energy arresting kind of equipment to keep people and equipment safe. That's usually why we get involved. Then, I would say the biggest single one of those aspects that I normally get involved with is when people say, we bought this thing and it doesn't work the way that we hoped it would. So here I'm not referring to something like a minerals processing facility, for example. The equipment that they've got on there, each one of those pieces of equipment are millions of dollars worth of money. And if it doesn't do what it's supposed to do, and there's a whole lot of wastage in there, you can imagine how much product is just thrown in the bin effectively, or stuck in the process somewhere, and it can't be accessed because it's in the middle of this thing, and this thing was designed really poorly. And so that's usually when we get involved, is to help people understand, first of all, well, what is actually happening, what physics are involved, especially things you can't see.
Yeah, that's right.
Cameras can do a lot for us, but it can't see into something that light doesn't emit out of, right? So if you can't see into a vessel, or if the thing that you're trying to look at, like the fluid or slurry that you're trying to look at, is simply non-transparent, then you can't see anything that's happening in there really.
Yeah.
So a lot of assumptions and gut feels and years of experience add to all of these things for sure. And that's not to say that simulation is always going to give you the right answer. In fact, I should probably make sure that I mention at some point today that simulation will absolutely give you an answer. The question why we're employed as engineers is to figure out, is the answer that it's giving me the correct answer for the problem I'm trying to solve?
It's the intuition that you're talking about as well. So learned experience or whatever. And a lot of these are things that we talk about are tools where simulation may be one of them, but what it can do is you got to test those intuitive assumptions in your gut feel as an engineer. And I think that's the wonderful balance between that sort of design or that sort of thinking, because as we think about systems, as we think about how we can model them, as we think about how they can work, as you said, people have their own set of problems or their own situation that they need to do to either model it or simulate it. It will always come back down to, okay, does this seem within the ballpark of what we're considering? That sort of, I guess, leads us onto the different types of the different things. I know there's a lot of three-letter acronyms that we'll throw around, but maybe for this section of the conversation, I can throw out a few, and you can talk to them one by one, or we can talk to them together, or whatever. Some of them that I can think of that we talked about before is FEA, CFD, DEM, DME, EMAG, optics. Probably I could go on and on.
Yeah.
Is there any ones that sort of hit the dartboard for you straight away? And I'd love to sort of come back and forth in between them. And
well, maybe we'll just quickly say what some of those are. So FEA is finite element analysis. It's nothing new. It's been around for I don't know, 100 years or so. I guess you can go back. It all really comes down to numerical methods. So back at university days and the mathematical background to this is using effectively linear algebra and calculus and so on to go solve physical problems. So it's applied mathematics really when you think about it. So finite element analysis is something that a mechanical engineer doing structural type work is probably going to use. Anyone making something that needs to be strong enough. If those are the things you're asking yourself, is this thing going to be strong enough? Is it going to deform or deflect a certain amount? Those kind of things you can answer with finite element analysis. CFD is computational fluid dynamics. So it's pretty much in the name, I'd say. That field in and of itself is so big that I would argue if someone were to say that they're a CFD expert, I would say, well, which part of it?
Yeah, exactly.
There's just so much to it. Like I don't know, we've got 6 CFD experts in our company and they are experts in various domains. That not always overlap. And
so just for my context, like CFD, when you say there's a lot of different aspects, what are the different aspects? I can think of one in my head is, it might be, tides and waves and other things like that, potentially. I don't know, lakes and streams, I don't know.
Yeah, those sort of things definitely form part of it. External aerodynamics over a race car. That's also CFD. A mixing tank or a what do you call it? Flotation cell, for example, in the mineral processing industry, where you've got particles suspended in liquid, and you're, I don't know, throwing in some pretty serious chemicals to try and reduce minerals out of it. That's also computational fluid dynamics. Flow in a pipe. Oil and gas industry, water industry, that's all fluid dynamics as well.
Maybe gas in pipes and like other...
gas as well. So steam for power generation, traditional steam turbines and those kind of things. Polymer flow, so injection molding, those kind of things is probably borderline still CFD as well, or could be considered as CFD. To some extent, you can almost say bulk material flow as well. Could be considered as, well, we wouldn't use the term CFD. We'd normally use one of the other acronyms, DEM, which is discrete element modeling.
Right. Now we're getting into that one. That's good.
The mathematics is slightly different. The way you formulate the problem numerically is slightly different. So you're treating each individual particle which could be something like, I don't know, Smarties or Astro. Do you know what Astros are in Australia?
No.
So it's something that I had a lot of as a kid growing up. It's
you got to bring some over for us.
It's kind of like an M&M or a Smartie or something like that, right?
Yeah.
Anyway, so you've got all of these particles and they're all interacting with each other. So you've got, a spring in a dashpot or damper describing the way that these particles interact with each other, bounce off each other and so on.
That's right.
And then you can start asking questions such as, let's say these particles represent iron ore that's flowing through a conveyor belt, on a conveyor belt, but then discharged through a chute onto something else.
Yeah.
And you're worried about things like what is the wear rate on this chute.
Yeah.
You could make those kind of predictions with
it's pretty interesting
with DEM.
Yeah, that's so you got FEA sort of. I think of FEA a lot about sort of materials and I obviously use strength of materials and material properties and elastic modulus and yield strengths and other things like that. I definitely use that a lot in my structural engineering practice.
Yep.
And that's certainly a go-to for a little bit more advanced analysis as opposed to just doing frames and beams and things like that. I haven't got into computational fluid dynamics, but I assume like from what you're talking about is that's more about fluid flow essentially.
Yep.
As it says in the name, but the law of thermodynamics and fluids and other things would certainly come into that.
Yeah.
And then DEM is discrete element modeling as well. So there was a couple of others as well. DME.
DME. So that's less direct physics. It's more of a system type approach. It's digital mission engineering.
Yep.
I'm trying to think of a good example to illustrate the context. Let's say you want to watch the AFL.
Yep.
And let's say the AFL is being filmed live in Melbourne, and it needs to be beamed across the country to Perth so we can watch it here.
Yep.
But let's assume that the satellites that we're beaming it across over is not a geostationary satellite, so it's not locked to a location on the Earth. Effectively, it's orbiting. And there's some thunderclouds rolling in, and this whole scenario is unfolding, right? While you're trying to watch your game, and you're just all you want to know is, am I going to be receiving a good enough quality signal on my computer,
or what's the score,
or what the score is, etc. Right?
Yeah.
So that is that you could classify that as a mission, and so you could say, well, on this day with these following weather conditions, with the satellites in these orbits, with a signal that's being sent from a specific location in Melbourne through its climate, so clouds and whatever else as well. This is not a climate modeler as such. I just want to make that point clear, but it's, so imagine you're trying to get the signal across through all the various chains that you need to get to
and other things.
And so you do this this time-based study to figure out if you're going to be receiving a signal on your computer or TV. That's what digital mission engineering is.
Yeah, right. Yeah. So it's really like it's really a strategic pulling together of the modeling for a specific purpose, I suppose.
Yeah. So I mean, you can take that. I was purposefully trying to create a civil, as in civilian type application, but you can imagine defense type applications.
Oh yeah.
So where you've got various different kinds of assets, and not just say satellites, but maybe you've got aircraft, and maybe you've got vessels and land forces and so on as well.
That's interesting, yeah.
And ultimately the question is, if we hit go on this mission, will we have mission success?
Yeah, okay.
Everything that's related in that. So the cool thing, what's really cool about these discrete physics that we can solve, one of them is EMAG that we touched on, touch on, which is electromagnetics, which is typically broken up into two domains, high frequency and low frequency electromagnetics. The divide between those two, or the split between those two, is around the megahertz range, if I remember this correctly. So let's just think about high frequency electromagnetics. That's communication. That's 5G, that's Wi-Fi, Bluetooth, all of that kind of stuff. So imagine you've got a transmitter sitting in Melbourne that needs to beam a signal up to a satellite that needs to receive that signal, and then beam it across maybe to a different satellite, and then beam it down to Perth again. The thing doing the beaming is the antenna, right? So that antenna has a very, very specific and designed radiation pattern. So you can simulate that. You can create a model, a 3D model of your antenna, apply the physics to it, see what the radiation pattern is locally around the antenna itself, and then propagate that through shooting and bouncing rates up technology. To get it up to, I don't know, 10, I don't even know what orbit satellites would go in, but let's assume 20 kilometers or something above the Earth. And see if you can get that signal at a good signal strength up there and then beam it across and then down again. So you can take these discrete simulations you've done for specific components that needs to do some work and put its performance metrics that was simulated into a mission and see, well, what if we've got some optics in this whole system chain? What if we got a sensor with lenses that maybe needs to do some thermal imaging? Will it actually be able to see the target? All of those kind of things. So that's what DME is all about.
Well, there you go. You've taken us on a journey of the 3-letter acronyms. Yeah. And I'd like what was striking to me is that a lot of these are very related. You know, you've got whether it be your computational fluid dynamics or CFD, and then the discrete element modeling. I'm sure you've got probably both of those together. If there's a fluid flow and if there's a discrete element flow there as well.
Couple simulations.
Yeah, a couple simulations. I could probably think of some mining applications that would certainly be along with that. EMAG, which you talk, electromagnetics, with that, and then there's optics with the light and other things like that. And it's interesting, you started to sort of list different applications or different project examples as such of like things that you could do to simulate. And one thing that really struck me as you're talking then and as we've talked previously is that it's actually interesting knowing the physics, knowing the laws of what governs those, and now having the capability to be able to, say, simulate those. It's interesting to think that there's not this narrow band of things that you can model. You can actually model a grander scale of things.
And well, that's definitely true. And something that we do a lot of work in as well is sometimes the simulation technology that we're using doesn't have the models available for the kind of problem that a customer brings to us.
That's right. Yeah.
So some of our experts, some of which are PhDs, some of which are professors at universities in Australia as well. So they carry a lot of technical authority, I would say, in their fields. Would then go and speak to the developers and build models and have examples and so on of what the physics need to, what the simulation software needs to incorporate to capture the physics that they're trying to solve. And so it's not just a one-way, here's simulation technology that was developed somewhere else in the world, and let's go and apply it into Perth, into our industry. It's the other way around as well. So you don't often necessarily hear this side of the story in industry, but big multinational vendors like the ones that we support certainly do pay attention to new technology development in fields that's not necessarily popular as such. Like it's not flashy, it's not Formula One cars or the latest and greatest civilian aircraft that needs to be developed. It's not that. It's dusty and it's mining and it's all that kind of stuff.
That's so true. And I think like you said, some of those players, they're certainly, I can imagine they're thinking about this sort of thing, in terms of a digital outlay or strategy around some of the things that they're working on. And traditionally, like even in my own consultancies, I've realized that, we use some pretty rudimentary tools, we use sort of empirical based standards to do things. We sort of tick the boxes on whether we comply or whether we don't comply. And a lot of the things that you're mentioning, are things that might be outside the box, but for maybe a mining giant that's moving hundreds of thousands of tons of ore, a percentage increase due to maybe some simulation and some understanding about the system would save them millions of dollars, in the scheme of things.
That's 100% true. And one of the things that we're noticing is that it's, we're both engineers. The typical personality makeup of an engineer is not someone that necessarily communicates well.
Yeah, that's right.
And hopefully, for the most part, they're fairly humble about what they're actually doing. We can, if you want to, we can go down the whole, like you mentioned, you brought up standards, for example, design standards and so on, which kind of, in my mind, activates the the component of engineering, which is morality as such. What are we doing, and is what we're doing responsible towards society in general? Standards exist for the purpose, in my mind at least, that's how I understand it, to keep the public safe from things that engineers design.
Yeah, exactly. Yeah.
That's what it's there for. It doesn't exist to describe fundamental physics.
Yeah, yeah.
So sometimes standards can be overly conservative, but they're also built such for a reason, because you don't know the intentions of every person that's going to be using it, or the ignorance of a person that's going to be using it as well. So you want to make it robust enough so that it would actually stand up in court, right?
Yeah,
that's the whole purpose of it. But there are industries that design and manufacture components. For example, a device that holds a microphone up. I don't think there's a very big risk to that hurting someone, causing injury, for example. So there's a place for standards, but it's not the only way to design things.
Yep.
I managed to get myself sidetracked there. But it's something that is very useful, but needs to be kept up to date as well.
Yeah, yeah. And also, like in my impression and things that I sort of believe is, I totally agree with that. We certainly need those that to be held to a high level of a standard, which is not just the baseline, but I think that's also striving for excellence. But it's also interesting that exploratory and curiosity that you can get out of different things such as this. And I actually was really, when we were talking before this, you showed me a few examples. One of them was you pulled it up and it was this heart beating, and I could see the flow of the blood through the aorta and the different valves and things like that. And I thought to myself, wow, that's pretty interesting. You can model a heart.
Yeah.
You can model the flow through a heart, and here I am just sort of modeling my beams, and I've got an I-beam and a bends, and it's not too flashy, but I sort of sat back and I realized, okay, whatever you want to sort of consider in the future, and whether it be an engineering task or whether it be a biomedical or other things like that, we can actually, with the fundamental physics that we have, conceptualize things that haven't been invented.
Yeah,
we can model those things to what we think the physics would be, and whether they be a product or whether they be something else that could, I guess, make life easier. There's this frontier where you don't just simulate things that are there; you can simulate things that aren't yet built. That's my impression. I don't know what you think.
Yeah, well, I mean, that's the whole idea, right? That's the whole journey you embark on if you're involved in research and development of products. You're conceptualizing something and solving a problem that hasn't necessarily been solved before, or you're improving something that has been solved before but was done to the level of technology or whatever technology entails, whether it's simulation technology or whether it's manufacturing technology or whether it's just no one thought about it before.
Yeah.
So that's the whole point of simulation, right? So we've got mathematics that describe things that we don't necessarily have applications or understand applications for yet. And that's how, that's something that's always fascinated me, is how we always, it seems to be the case that things start with mathematics. Mathematical models and mathematicians try to explain things and discover new things in mathematics that physicists then go and find applications for.
Yeah, that's right, yeah.
And then that eventually trickles down to engineers to go and make stuff.
Yeah, yep.
Hopefully for the betterment and improvement of every human being on this planet and the ones to come as well. We've gone down the moral path again.
Yeah, there you go. No, it will come back to it too. I think if we were to jump into a few examples, you might not speak to specific projects or whatever it is, but what I'm keen to do is maybe do a short fire. Okay, this is the example, and these are the different applications, whether it's FEA, CFD, or whatever it is. So if you were to say like an iron ore bulk material through chutes, could you take me through maybe some of the different systems that you might use in your modeling? Simulations.
So typically a question would come up. We're always trying to solve a problem, right? So the problem formulation could be something like, we are worried that this particular chute is going to clog up. When we put a specific kind of material through it. Normally the way that I would respond to that question is, do we understand what the material properties are for the bulk material? So this is something you can send to a lab, and we have customers amongst others that do these or provide these kind of services to industry, that then go and get these bulk material samples tested. They do things like angle of repose test, where you put some material into a tube and you gently lift it up and you look at the angle that it forms as it's creating a pile. That gives you an indication of how well or not well particles want to stick to each other or not. So it gives you that sort of understanding. Now, there's so many different things that influences that particular behavior that you see from particles, but it turns out that you can make very good guesses of the material properties if you do these kind of fairly basic tests. So once we've got the material properties captured and we know what properties we need to tell the physics to use, then we can go and describe the domain. So we need a 3D CAD model, for example, that describes what the chute looks like and where they've got, I don't know what the right terminology is because I'm not a chute expert, but let's just say baffles. So these are plates that are, so chute typically, for those who don't know, it normally gets a feed from a conveyor belt at the top, and then it redirects the flow of these rocks effectively down some kind of a metal structure onto another conveyor belt typically, or whatever else they need to send it on, whether it's just a bin or a silo or whatever it could be. And if that thing clogs up, it means that you keep pumping in material with a conveyor belt, but nothing's going through. And eventually the whole thing just spills over and creates this massive mess, something your kids could never replicate. And someone needs to go and clean it up. So the whole facility needs to shut down. So there's a lot of cost involved with getting this wrong. So now we've got the material coming in. So we've got the material properties calibrated or captured, at least tested. Then we've got a 3D CAD model that describes what the domain looks like. Then we need to understand some operating conditions. So how fast is the material traveling on this conveyor belt? Obviously at which angle and so on as well into the chute, so that you can again tell the software this is how fast things are going to be moving. This is the inlet velocity, for example. And then you need to describe things like, well, how do I want the particles to interact with each other? Some of that stuff is captured in the material properties, but some of them you need to switch on specific material models. That describes the way the particles interact with each other, because some particles might want to clump together, others, under certain circumstances, and others, will break apart and so on.
And this is under the sort of discrete element modeling.
That's all part of discrete element model. And so you could then run the simulation. Typically, these simulations we would run on a GPU type computer setup. So this particular type of physics lends itself very well to GPU solving. Here I'm not necessarily talking about gaming cards. I'm talking about compute cards as well. In fact, more so compute cards. So the very expensive ones. Gaming cards can be used to some extent with some success, but anyway. And then the response from the simulation would be that you can visualize what's happening with these particles and whether it is in fact looking like it's going to clog up, or in fact does clog up, or if you've got stagnation zones where there's a deflector plate, but all that happens is all the material goes and accumulates on it, and it creates effectively a sandbank, if you would, if you want to think about it from a channel flow example. And so you can then decide, well, do I want to change the angle of those deflector plates?
You can make decisions.
Run it again. And eventually, once you've decided that you've kind of converged on a design that you think is going to work well, you might decide to test slightly different material properties. Because maybe the sun is hot and the moisture content is a little bit less, so it's a little bit drier. What'll happen then?
And so you can test different scenarios, I suppose. And sort of iterate or work on the model or the simulation in such a way that sort of helps you make those decisions in certain areas. Because you can pull different levers, I suppose, at different ends of the system, right? You've got whether it's coming in drier than it should be, or whether you need to cover it up, or like there's physical different things. So you can make a lot of decisions from a model such as that.
Yeah, and we'd refer to that as a parameter study.
Yeah, great.
Which kind of leads us into one of the 4-letter acronyms, PIDO, which is Process Integration and Design Optimization.
Yeah, let's dig into that. Yeah.
So that is, once you've got a problem described, and here I'm referring to a problem that is maybe, that's got a single set of input variables and model definitions. So model definitions would be the physics that describes what's happening.
Yep.
And maybe even a single geometry iteration. So you've got one chute that you want to send some stuff through. And you've got one material test that calibrates that particular material. So you've got one setup, right? Then you can say, well, all of these numbers that we're feeding into the software that describes the bulk modulus or density or something like that of the material, or the, I don't know, plate thicknesses, or the size of this particular dimension of the chute, like the length and the width and the height, and those kind of parameters. You can decide which one of these different things that drive the model, parameters that drive the model, are parameters that can be modified by yourself, or you can tell a computer to do that for you and say each one of these parameters has a minimum and a maximum, so an envelope that it can change in. And you can ask through a process called design of experiments. You can go and fill this multi-dimensional parameter space with discrete values for each parameter that fills the whole multi-dimensional space. In other words, you've got, I'm not describing this very well. So let's say the material properties can change from 1 to 10. And it can take up any number in between there, because the moisture content could be, continuously variable depending on what the moisture content is for the material, or the length can be any value between 1 and 10 as well. So you say, I want to seed 100 simulations, and those 100 simulations should be some combination of all of these parameters. But it should be done in a clever way, so that we don't just simulate 100 simulations with the material variable set to 1 while everything else is changing, because it means you've not discovered anything on what the material property does.
So you can see some of the bounds of your different simulation and what you're trying to, the different levers you're trying to pull.
And we'd refer to that as a sensitivity study.
That's right.
So parameter sensitivity study is what you're effectively doing. That helps you understand the operational and design envelope of your system that you're simulating.
And the design envelope in terms of the different parameters that you can pull, the different, I guess, sizes of that system, or different inputs and outputs of the system as well.
And if you're familiar with, say, race car or motorbike racing, where tires is always the thing that they're complaining about, like which tires to use and are they going to last long enough and all of those things. You can imagine how many parameter studies are done in the background. To figure out, for the track temperature on the day that we're racing, what is the expected life of these tires that I'm riding on? Because you've got models that describe these things. You can relate the wear on the tire to things like, well, what is the lateral acceleration? What is the acceleration from the motorbike? So radial acceleration as well. And you can relate all of these things to wear of the tire.
That's right.
So that's what we do.
So I like that. So the process integration and design optimization, I think that's a really, really good piece, because what it does is it actually brings together a lot of the different types of simulation that you're talking about, which is like the FEA, the CFD, the DEM, and you can bring together all these different components. We've talked about some mining applications. We've talked about maybe some biomedical applications with the heart. We've talked about some electromagnetic stuff with satellites and other things like that. And I think what that does is it gives us a broader picture of what can be accomplished. And I think we touched on that just before. And I think for me as an engineer, being aware that, okay, these things are actually happening, and particularly in fields such as like a more nuts and bolts engineering, you don't often think that there is this platform of simulation that you can tap into. I think there's probably engineers that often come up to a brick wall and they're like, oh, we can't go anywhere past this, And from there, it's sort of like what do we do now? But there is a tool that we can use, which is that simulation. What I want to do to focus on for the last part of this conversation is just to really think about that mindset, think about simulation as a bit of a superpower that you can take on. We talked about the different applications, different industries and other things like that. And then maybe a bit of a forward-looking view just to sort of wrap it up. But I guess for yourself, what do you think that sort of forward-facing view is, and what's your impression around some of these tools using simulation for an engineer?
I'd say there's about 3 or 4 things that I would love to share with you while thinking about this. And it really needs to go back to, I would say, to students and the interest that we share with students, with new prospective engineers and physicists and mathematicians and so on. We have to create this awareness that this is really cool. This is we're doing this because it's fun and it's challenging and it's interesting, but we're also making other people's lives better, which brings me. So that's sort of the first point, right? We need to really put a focus as an industry on our students and the next generation that's coming through as well, mentorships and all those kind of things. The next thing I would say is you're part of a community. Yes, it could potentially be a superpower. And any one of these different things that we're doing as an engineer, in my case, for example, experimental test and measurement, that could be a superpower as well, because you get to actually measure. My previous boss used to say, to measure is to know. So all of these different aspects and tools that we use as engineers are useful, but they are just that. They're a tool. The superpower lies within the fact that you're part of a community of other people, of scientists that's come before you, engineers that's come before you, the giants of old, if you would, on whose shoulders we're all standing, right? Now, there is also the fear of the unknown. And how do you, I can imagine someone saying, how do you expect me to trust simulation if I've never seen it work? And I would say that's a very, very valid criticism. So I don't know what that would look like for every person. In my case, it was, like I said at the start of the discussion here, is my career started where I was able and very fortunate to be able to find that correlation between the experimental test and measurement world, where you go and measure stuff and the whole science of creating measurements and so on, and then relating that to a numerical model that is on a computer that doesn't know anything about the fact that you were just in a lab doing some testing, but they give you the same answer if you do it properly. And if you apply all the principles that the giants of old have taught us and have laid down for us and have described for us. So that community is very important. And so it can be very isolating to go down this path. There's the age-old example of an engineer that's being locked away in a dark room and just supposed to produce answers, sort of thing. But we are all humans, and we share in passions and things. And the community is very good because other people have solved problems that you haven't thought of yet. And you were mentioning, coming up a brick wall. Someone else might have figured out how to get around
That's
it,
right. Yeah.
or just break it down, or whatever the case might be. But you can, if you have a community, you can ask these questions.
Yeah, that's right.
And so that's one of the things that I'm very passionate about as well, is how to establish this community. I can only really influence where I am geographically. So we've got this technology day, simulation technology day, if you would, that we're putting up in about 30 days from now.
Yeah, great.
Give or take. So the 30th of July, we'll have it. They're in South Perth, in one of the suburbs there. And we'll have people from industry coming to give a quick 20-minute discussion on what they're doing and how they're using simulation. And a little bit earlier in this conversation, we were talking about engineers typically not being very good communicators. And one of the things, and that they tend to sometimes be humble, sometimes not, but they tend to undersell the value of what they're doing, if they sell at all, within their organizations. And it's something I would encourage everybody to do, is just you are valuable in your role as an engineer. Find a way to communicate that without becoming, a megalomaniac and full of pride and all that kind of stuff. So keep your humility, but find a way to communicate it, because there's value in what you're doing.
And share with the community.
Exactly. The value could be something like, we're able to reduce the cost of designing this thing or operating this thing, or unplanned shutdowns that would have cost us millions, but we were able to circumvent that because we did some work up front. We did some experimentation. We did some simulation. We did calculations, whatever it might be. Right, but let people know in a humble but clear way that you're adding value.
Yeah, that's right. That's great. And look, I appreciate your perspective on those sorts of things. And I for like outwardly looking, I think that is so important, the community piece of it. And we cannot do this in isolation.
And that's what you're doing with this podcast.
Yeah, that's it. Yeah.
Yeah.
Just I think sharing stories, sharing experiences, sharing what can be done is a really optimistic way of looking to the future. So I'd like to finish up. We usually hand it over to the AI host. So I'm going to hand it over now. He'll summarize a little bit about what we talked about, but he's just going to ask you one last question and then we'll close up.
Yeah.
If that's all right. So see if this works. All right. I'm going to hand you over now to the AI host.
Thank you, Owen. Simulation is not just a mirror to the real world. It's a rehearsal space for better decisions. Today's episode showed us that when we can digitize the physics of a system, whether that's a stream, a valve, or a conveyor chute, we're not replacing engineering judgment. We're empowering it. Derik reminded us that simulation isn't just about speed or efficiency. It's about depth, the ability to see complexity, test it, and refine it before the first bolt is tightened. And as engineers, that gives us something rare, the space to ask, what if? What if we could design with less waste? What if we could catch failures before they happen? What if our best ideas don't need to wait for a prototype? If this episode sparked something, stay with us. We're just getting started. In future conversations, we'll keep unpacking what modern engineering really looks like, not just on paper, but in practice.
All right. It was supposed to ask a question.
I noticed there was no question in there, but I thought that was a very good summary.
It's not a bad summary, eh? Not a bad summary at all.
I would maybe say in summary, we didn't really talk about the whole AI topic, but simulation and AI is a topic to be discussed. And we can maybe, in the future delve into that as well. The one thing I would say that has become very, very clear to me recently, as an engineer, I can't speak for other domains and industries and applications, but AI within simulation, it is, to the best of my knowledge, it is absolutely the case that an AI can lie. Not because it wants to necessarily, but because it might be taught on information that is incorrect. So if you expect to get the truth out of an AI because it was taught on everything out there on the internet, presumably, it will generate an answer. The same as simulation. It will generate an answer because it can crunch some numbers and it can spit some things back at you. And I would encourage people to just remember that an AI is a tool that is that's fundamentally just tracking the probability of, in the case of a large language model, of certain words appearing next to other words.
Yeah, that's right. Yeah.
And if we teach it, like it's being taught on the things that we feed it, right? So if we feed it with garbage, it's gonna give us garbage back.
Yeah.
And that's exactly that's an age-old thing within the simulation world. If you feed it with bad parameters, bad information, bad material models, it's gonna give you an answer, but it's gonna be garbage.
And look, and I agree with you. That's the sort of chapter 2, I reckon, in terms of a conversation that we could have, because we talked about the design optimization piece.
Oh yes.
And I think where it's going, particularly with AI, machine learning and other things like that, I'm very optimistic with that. But again, Derik, I really appreciate having you on the podcast, and I think it's been a great discussion. I really appreciate your perspective on a lot of things, and I think we'll close up now. Is there any final words that you want to share with us?
Oh, I would just thank you for this opportunity and the fact that it's that you're doing this. I think it's great to have this as a community, as part of the community.
Yeah.
So yeah,
great. All right. Thank you again.
No problem. It's good
Cheers.
fun.